Every great city on Earth is a testament to our ambition to build upwards, to reach for the sky. We measure our progress in the height of our skyscrapers, in the gleaming glass and steel towers that punctuate the horizon. But this vertical world, this city that we see, is an illusion. It is a facade. The truth is that for every meter we build towards the sun, we must first conquer the darkness below. The entire weight of our civilization, its commerce, its culture, its crushing physical mass, rests upon a hidden, horizontal world, an immense and intricate subterranean landscape that is arguably the single greatest and least understood engineering marvel of the modern age. This is the story of that world, the story of how we build the impossible passages that are the true arteries of the metropolis. The very ground beneath your feet is not the solid, dependable constant you imagine it to be. It is a membrane, a thin, carefully engineered skin, separating the chaotic life of the surface from the silent, high-pressure world of the deep earth. Through this membrane, we have threaded a network of passages of almost unimaginable scale and complexity. While you work in an office tower, a river of steel, a subway train carrying 1,000 people, may be gliding silently through the bedrock 100 meters below. While you sleep in your bed, a torrent of fresh water, the lifeblood of millions, is rushing through a concrete vessel wide enough to drive a truck through, its path charted through the earth with millimeter precision. We live our lives on the surface of a drum, blissfully unaware of the profound and thunderous work that is required to keep it from collapsing. This is an exploration of how that work is done, not with magic, but with mathematics, geology, hydraulics, and brute mechanical force on a scale that borders on the unbelievable. We will journey down past the familiar layers of asphalt and concrete and into the earth itself, to understand the science, the risks, and the sheer audacity of modern urban tunneling. Before we journey further, feel free to leave a comment with from what location you're watching this, and what time it is here. Now, settle in, as our exploration truly begins. Our descent does not begin in soft earth, but in a dense, man-made archaeology. The first few dozen meters beneath any major city are not a natural geology, but a chaotic landfill of its own history. Here lie the ghosts of forgotten infrastructure, crumbling brick sewers from the Victorian era, abandoned pneumatic mail tubes, stone foundations of buildings that no longer exist, and a tangled, uncharted web of old pipes and cables laid down by generations who kept poor records. This is the first great challenge. Before a modern tunnel can even begin its journey, its path must be cleared through this treacherous historical debris. It is a painstaking process of mapping the unknown, of using ground-penetrating radar and carefully drilled boreholes to create a three-dimensional image of the unseen obstacles. It is less like construction and more like performing a delicate, high-stakes surgery on the city's past. Deeper still, we leave the realm of human history and enter the realm of geological time. Here, the challenges are more fundamental and far more powerful. The ground is not a uniform homogeneous substance. It is a complex layer cake of different materials, each with its own unique and often malevolent personality. There are layers of soft, waterlogged sand waiting to liquefy and flow into any new opening with the force of a tidal wave. There are pockets of hard, abrasive granite, capable of grinding the most powerful steel cutting tools into dust. And there are beds of stubborn, sticky clay, which can clog and suffocate even the most advanced digging machines. Most dangerous of all is the water. The earth is saturated with it, and this groundwater is often under immense pressure. The single greatest fear of the tunneler is a breach, an uncontrolled inflow of water and earth that can lead to catastrophic collapse, not only of the tunnel itself, but of the very surface of the city above. To conquer this high-pressure, unpredictable, and completely invisible world, we have conceived and built one of the most extraordinary machines on the planet. It is not merely a digger, it is a self-contained subterranean starship, a mobile factory designed to navigate the hostile environment of the deep Earth. This is the tunnel boring machine, the TBM. Its scale is difficult to comprehend. A machine that can be over 150 meters long, weighing in excess of 4,000 tons. At its front is the cutter head, a massive rotating steel disc, bespoke for the geology it will encounter, armed with an array of hardened steel discs and tungsten carbide scrapers that spin with enough torque to pulverize solid rock into something that can be transported. Behind this immense grinding face, the machine is a marvel of complex systems. It has hydraulic rams that press against the tunnel walls to thrust it forward, a sophisticated laser guidance system to keep it on its precise preordained path, and an automated factory that erects the permanent precast concrete lining of the tunnel in its wake. It is a mechanical beast that simultaneously destroys the earth in front of it and creates a perfect permanent structure behind it. But the success or failure of a multi-billion-dollar tunneling project, the safety of the workers, and the stability of the city above all depend not on the power of this machine, but on knowledge. Before the first grain of sand is moved, before the first piece of this steel titan is lowered into the earth, there is a long, silent, and critically important period of investigation. The tunnelers must come to know the ground they wish to conquer with an almost perfect intimacy. They must understand its weaknesses, anticipate its movements, and predict its behavior under the immense stress of their operation. The first great act of building a tunnel, therefore, is not an act of construction at all. It is an act of deep and meticulous exploration. For how do you prepare for a battle against an enemy you cannot see, whose weight is measured in millions of tons, and whose temperament is a mystery written in the language of deep time? You prepare for this battle against an unseen geological titan not with shovels, but with information. Before a single ton of steel is ordered, before the first designs for the tunnel boring machine are finalized, a long and silent war of intelligence is waged. This is the domain of the geotechnical engineer, a unique breed of scientist and detective, whose job it is to build a perfect high-resolution three-dimensional map of the subterranean world. This is arguably the most critical and highest stakes phase of any tunneling project. The data gathered here, in the quiet months and years of investigation, will determine the design of the TBM, the method of excavation, the type of tunnel lining, and ultimately, the success or failure of the entire multi-billion-dollar endeavor. A mistake here, an undiscovered layer of soft ground, a miscalculation of water pressure, can lead to a cascade of failures so catastrophic they can bring a machine and a city to a grinding halt. The work is slow, meticulous, and happens almost entirely out of the public eye, but it is the true foundation upon which all subsequent work is built. This intelligence gathering does not begin with the rumble of a drill, but with the quiet rustle of paper in the hushed halls of city archives. The geotechnical team becomes a group of urban historians, embarking on a deep and often frustrating paper chase to unearth the ghosts of the city's past. They hunt for centuries-old municipal maps that might reveal the path of a long-buried river or stream, a feature that, though now invisible on the surface, still exists below as a treacherous channel of waterlogged, unstable soil. They search for old geological surveys, mining records, and even construction plans from nearby buildings, looking for anecdotal evidence of the ground conditions encountered by those who have dug there before. They pore over historical photographs, searching for visual clues of a forgotten quarry or an old industrial waste site that was filled in and built over 100 years ago, now existing as a hidden pocket of soft, unpredictable, and potentially toxic material. Every piece of information, no matter how obscure, is a vital clue. Another small pinprick of light in the immense darkness of the unknown. They are building a case file on the Earth, cross-examining its history to understand its present-day temperament. Once this historical tapestry has been woven, the physical investigation begins. Often in the dead of night to avoid disrupting the city's rhythm. Small, unassuming drilling rigs are brought onto the streets and sidewalks along the proposed tunnel route. From these positions, they begin to pierce the veil, drilling a series of boreholes deep into the ground. These are not just holes, they are precise surgical incisions designed to extract physical evidence. As the drill advances, it brings to the surface long cylindrical cores of soil and rock, perfect cross-sections of the subterranean world. To the trained eye of a geologist, these cores are like a library of deep time. They reveal the story of the Earth in vivid, tactile detail. The sharp, clear line separating a layer of dense, reddish clay from a stratum of pale, fine-grained sand. The cool, solid heft of a piece of granite, its crystals glittering under the work lights. The damp, musty smell of earth that has not been touched by air for millennia. Each core is meticulously logged, photographed, and sealed in protective tubes. Its exact depth and location recorded with GPS precision. Dozens, sometimes hundreds of these boreholes are drilled, each one a vital data point in the slow and patient process of mapping the abyss. These extracted cores are then transported to a geotechnical laboratory, a place where the Earth itself is put on trial. Here, the silent, inert samples are subjected to a battery of rigorous tests, a scientific interrogation designed to force them to reveal their secrets. Sections of rock core are placed in immense hydraulic presses and crushed to determine their unconfined compressive strength, a measure of the raw power that will be required to break them apart. Soil samples are analyzed for their particle size, their plasticity, and their moisture content, which dictates how they will behave when excavated. Will they be stable, or will they flow like liquid? Other samples are subjected to permeability tests, where water is forced through them under pressure to determine how easily the groundwater will be able to invade the tunnel. The abrasiveness of the sand and rock is measured to predict how quickly the brutally expensive steel cutters on the TBM will be worn down and need replacement. Even the chemistry of the groundwater is analyzed to check for corrosive sulfates or chlorides that could, over the span of a century, eat away at the concrete and steel of the finished tunnel lining. While the boreholes provide deep, vertical snapshots of the ground, the spaces between them remain a mystery. To fill in these gaps, engineers deploy a range of sophisticated, non-invasive techniques, a field known as geophysics. They conduct seismic surveys, laying out lines of sensitive microphones on the surface and then creating a small controlled vibration, often from a specialized heavy truck. By measuring the time it takes for these sound waves to travel down, reflect off different geological layers, and return to the surface, they can create a blurry but continuous ultrasound image of the rock strata. They use electrical resistivity, passing a current through the ground between two probes. Since water-saturated soil conducts electricity far better than solid, dry rock, this method allows them to map out the location of potentially dangerous underground aquifers and water pockets. This combination of high-tech remote sensing, akin to giving the city a CT scan, allows the engineers to build a more complete, holistic picture of the challenges that lie in wait, turning a series of disconnected data points from the boreholes into a coherent and continuous map. The final result of this long and multifaceted investigation is the creation of a ground model, a comprehensive, three-dimensional digital twin of the subterranean world through which the tunnel will pass. All of the disparate data streams, the historical maps, the hundreds of borehole logs, the thousands of laboratory test results, and the geophysical surveys are fed into powerful computer software. The result is a stunningly complex and detailed virtual reality, a block of the Earth that engineers can digitally fly through, examining every layer of rock, every pocket of sand, and every potential water hazard from any angle. They can use this model to run simulations, predicting how the ground will shift and settle as the tunnel is excavated, a phenomenon measured in millimeters that can have a profound impact on the buildings on the surface. This digital model is the single most important document in the entire project. It is the tunneler's Bible, the grand strategy map that will dictate every major decision to come. It transforms the unknown hostile abyss into a known, quantifiable, and ultimately conquerable environment. But sometimes, knowing the enemy is not enough. Sometimes, the ground revealed by this meticulous investigation is simply too weak, too unstable, or too saturated with water to be safely tunneled through. In these cases, the engineers must engage in one of the most audacious and impressive feats in all of civil engineering. They must change the very nature of the ground itself. This is known as ground conditioning. If the path lies through a section of treacherous, waterlogged sand, they may opt for ground freezing. This involves drilling a series of pipes into the unstable area, and then circulating a supercooled brine through them for weeks, slowly drawing the heat out of the earth until the groundwater freezes solid, creating a massive, temporary, but incredibly strong and completely waterproof block of ice through which the TBM can safely pass. In other cases, they may use grouting, a process where a specially formulated concrete-like slurry or a chemical resin is injected into the soil under high pressure, filling the voids between the grains of sand and soil, and effectively turning the weak ground into a solid, stable mass. This is engineering at its most elemental, the power to transform the earth to suit our needs. With the invisible battlefield now fully charted, its hidden dangers exposed, and its weakest points artificially strengthened, the silent war of intelligence is over. The stage is now set for the first great act of physical creation to begin. The plans are finalized. The path is clear. But this first act is not the boring of the tunnel itself. It is the construction of its birthplace. A colossal reinforced concrete cavern must be excavated deep within the earth, right in the heart of the city, to serve as the assembly chamber and launch pad for the tunnel boring machine. This structure is the portal, the gateway to the deep earth, and it presents its own immense challenge. How do you dig a hole the size of a small cathedral in the middle of a congested metropolis, surrounded by skyscrapers and saturated with groundwater, without everything on the surface caving in? The answer to how you dig a hole the size of a cathedral in the heart of a city is one of the most elegant and counterintuitive truths in all of modern engineering. You do not dig a hole at all. To simply excavate a vast open pit in the soft, saturated, and unstable ground of an urban center would be to invite immediate and catastrophic collapse. The immense, unseen pressure of the surrounding earth and water would surge into the void, undermining the foundations of nearby skyscrapers and turning the streets above into sinkholes. Instead, the problem must be approached with the meticulous foresight of a grandmaster playing chess. The walls of the great cavern must be built first, materialized deep within the earth as if by magic, forming a fortress against the planet's pressure before a single significant shovel of soil from within that fortress is ever removed. This is the great secret of urban excavation. To conquer the void, you must first construct its cage. This colossal undertaking begins not with a display of power, but with months of quiet, painstaking preparation on the surface. The designated site, a cordoned-off section of the city, is first subjected to an intricate and delicate operation known as utility diversion. This is the unsung and immensely complex task of identifying and rerouting the dense web of subterranean veins and arteries that keep the city alive. Teams of specialized surgeons of the street, must carefully excavate, cut, and divert massive water mains, high-pressure gas lines, critical sewer trunks, and the fragile, indispensable bundles of fiber optic cables. Each one of these systems must be rerouted around the perimeter of the future launch box, a process akin to performing a complex bypass surgery on a living patient, all while ensuring that the city's circulation is never interrupted. Simultaneously, the site is armored for the immense construction to come. Acoustic barriers are erected to shield the surrounding neighborhoods from the noise, and sophisticated dust suppression and water treatment systems are installed. This is the slow, unglamorous, but absolutely vital prelude to the main event, ensuring the city can continue to function completely unaware of the immense operation being staged in its midst. With the site prepared, the construction of the unseen walls begins, often using a remarkable method known as diaphragm wall construction. Imagine a deep, narrow trench, perhaps only a meter or two wide, but plunging 50 or 60 meters into the earth. This trench is excavated not all at once, but in a sequence of discrete rectangular panels using a colossal, heavy-jawed mechanical grab called a clamshell. As this machine slowly and powerfully bites its way into the ground, the trench it creates is not left open to the air, where it would immediately collapse. Instead, it is kept completely filled at all times with a thick, heavy, and viscous slurry made from a special volcanic clay called bentonite. The immense weight and density of this muddy fluid exerts a constant outward pressure on the trench walls, perfectly counteracting the inward pressure of the surrounding soil and groundwater, holding the excavation open with its sheer hydrostatic force. Once a single panel is excavated to its full staggering depth, an immense cage-like skeleton of prefabricated steel reinforcement, weighing many tons, is lifted by a crane and slowly, carefully lowered into the bentonite-filled trench, sinking through the thick fluid until it is in its final position. The final step in creating a single wall panel is an act of alchemical transformation. A long vertical pipe, known as a tremie pipe, is lowered to the very bottom of the slurry-filled trench inside the steel cage. Then, a specially designed high-strength concrete is pumped down this pipe. As the concrete begins to fill the trench from the bottom up, its immense density and weight displaces the lighter bentonite slurry, which is pumped out from the top and saved for reuse. This process continues for hours. A slow and continuous pour, until the entire trench is filled with a solid column of steel reinforced concrete. This procedure is repeated, panel by interlocking panel, around the entire perimeter of the site, over a period of many months. A continuous, seamless, and fantastically strong concrete box, a subterranean fortress, is constructed deep within the earth, its existence completely invisible from the surface. It is a structure of immense strength and integrity, built by displacing a temporary fluid with a permanent solid, all before the space it contains has even been created. In different ground conditions, an alternative and equally ingenious method may be employed to form this subterranean barrier: the construction of a secant pile wall. This process involves the use of a powerful, large-diameter drilling auger. The machine first drills a series of primary or female piles in an alternating sequence along the wall's perimeter. These initial holes are then filled with a relatively weak, unreinforced concrete. Once this primary set of piles has cured, the drill rig returns and drills a second series of male piles in the gaps between the first. The key to this method is that the auger for the male piles is slightly larger, and it is positioned so that it precisely cuts into or bites the edge of the two adjacent female piles on either side. These new overlapping holes are then fitted with a steel reinforcement cage and filled with high-strength structural concrete. The result of this meticulous, overlapping process is a continuous, interlocking wall of vertical concrete cylinders, forming an immensely strong and, crucially, watertight barrier against the surrounding ground. It is another way to achieve the same goal, a defiant act of creating a solid before creating the void. Only when this massive, buried, and fully completed concrete cage is in place can the great excavation truly begin. Now a fleet of excavators, loaders, and trucks descends into the enclosure and begins the monumental task of digging out the earth from inside the box. As they dig deeper and deeper, the immense pressure of the surrounding earth begins to push inwards on the newly exposed diaphragm walls. To counteract this force, the cavern must be braced. At predetermined depths, massive horizontal steel beams known as struts are installed across the width of the excavation, pushing back against the walls and holding them in place. These struts, some as thick as a person's torso, are themselves supported by horizontal steel beams called wallers that run along the length of the wall. As the pit deepens, a dense, crisscrossing lattice of these enormous steel beams is installed, transforming the growing cavern into a stunning cathedral-like space of immense scale and complexity, a testament to the colossal, invisible forces being held at bay. As the excavation plunges below the natural water table of the city, the battle against water begins in earnest. The completed walls are watertight, but the ground at the bottom of the pit is not. Water begins to seep up from below, under immense hydrostatic pressure. To combat this, a powerful dewatering system is engaged, a network of deep wells and pumps that constantly work to draw down the local water table, keeping the vast construction site remarkably dry. Once the excavation reaches its final planned depth, the last major structural element is created, the base slab. This is the floor of the launch chamber, a massive solid slab of steel reinforced concrete, often many meters thick. This base slab must not only be strong enough to support the weight of the multi-thousand-ton tunnel boring machine, but it must also be heavy enough to resist the constant, buoyant uplift pressure from the groundwater below, which is perpetually trying to push the entire concrete box up out of the ground, as if it were a boat. When this final element is cured, the work is complete. Hidden deep beneath the traffic, the noise and the life of the city is a new and permanent place, a vast, silent, and cavernous concrete hall. It is a dry, secure, and structurally perfect environment, a pristine industrial cathedral, hundreds of meters long and dozens of meters deep, equipped with massive overhead gantry cranes that run along its length. It is the largest, most expensive, and most complex empty room in the entire city, and its sole purpose is to serve as a clean room, an assembly hall, and a launch pad for the Titan that is to come. The great void has been successfully carved from the heart of the city. The surgical theater is now prepped, scrubbed, and ready for the main operation. All that is missing is the star of the show. The great concrete cathedral now lies waiting, a silent, empty space of immense potential, hidden from the world above. But its star, the tunnel boring machine, is not a single entity that arrives on a truck. It is a colossal and incredibly complex machine that is forged in dozens of factories in different countries around the world, and which will arrive at the site in hundreds of individual pieces. The cutter head alone, a single disc of steel, can weigh over 100 tons. The main bearing, the component that allows the cutter head to rotate, is itself a masterpiece of precision engineering the size of a small house. How then do you choreograph the complex logistical ballet of delivering these massive multi-ton components through the congested streets of a modern city? Lower them one by one into the deep earth with the delicate precision of a watchmaker, and assemble them in the correct sequence to create the single largest and most powerful mobile machine on the planet. The answer to this grand logistical challenge lies in understanding that a tunnel boring machine is not a product one simply buys. It is a global project one orchestrates. These titans are not built on an assembly line. They are bespoke, one-of-a-kind creations, with each major component engineered and fabricated in a different corner of the world. In the few specialized factories with the immense machinery and expertise to create such colossal parts, the massive high-precision gears of the main drive might be forged in the industrial heartland of Germany. The complex hydraulic systems may come from a specialist in Japan. The sophisticated electronic guidance and control systems from Switzerland, and the immense curved steel plates of the main shield from a foundry in China with the capacity to roll such thick, heavy steel. The first great act of assembling the TBM is therefore a global puzzle, a masterpiece of project management that involves coordinating the intricate timelines of dozens of independent manufacturers, and then choreographing the complex dance of global shipping to ensure that hundreds of massive, unique, and irreplaceable components all begin a journey that will converge at the right time and in the right order on one single, small, cordoned-off patch of a distant city. The physical journey of these components is an engineering marvel in its own right, a hidden and heroic chapter in the story of any tunnel. A single, fully dressed cutter head, the face of the machine, can weigh hundreds of tons. A single section of the main shield is the size of a small house. These are objects that exist at the very limit of what our global transportation infrastructure can handle. Their journey begins on specialized, heavy-lift cargo ships, which are carefully ballasted to ensure stability while carrying such immense and unbalanced loads across the oceans. Once they arrive in a port, they are transferred to the land, and here the true logistical ballet begins. The components are loaded onto custom-built, multi-axle modular transport trucks, immense centipede-like vehicles with dozens of independently steerable wheels, designed to distribute the colossal weight. The journey from the port to the construction site, often a distance of only a few kilometers, can take days. It must happen in the dead of night, when the city's traffic is at its lowest ebb. The route is planned with military precision, requiring temporary removal of street furniture, traffic lights, and overhead power lines. Bridges along the route must be surveyed, and sometimes temporarily reinforced to bear the load. It is a slow, crawling procession, a parade of giants inching their way through the sleeping city, a vast and expensive undertaking that is the necessary prelude to the even vaster undertaking to come. The moment of transition, when these colossal pieces leave our surface world and descend into the subterranean realm, is a time of immense tension and breathtaking precision. Presiding over the vast open maw of the launch cathedral are the gantry cranes, immense, powerful machines installed for this single purpose. One by one, the components of the TBM are brought to the edge of the pit. Enormous fabric slings and high-tensile steel cables are meticulously attached by a team of specialist riggers. Then, with agonizing slowness, the crane's motors engage, and a piece of the Titan, a 100-ton section of the shield, is lifted from its transporter. For a few long moments, it hangs suspended in the air, a colossal piece of advanced engineering caught between the sky and the deep earth. The crane operator, guided by signals from the riggers below, then begins the descent, lowering the component with a steadiness and precision measured in millimeters. This process is repeated hundreds of times, a slow and deliberate population of the void, each lift a potential point of catastrophic failure. Each successful placement a small but crucial victory in the assembly of the giant. Down in the concrete quiet of the assembly chamber, the beast begins to take shape, and its assembly always begins with its heart and its skeleton. The first pieces to be assembled are the curved, immensely thick steel plates of the main shield, the cylindrical body that will protect the machine and its crew from the crushing pressures of the earth. These sections are lowered, carefully aligned, and then joined together with hundreds of massive, high-strength bolts, torqued to a precise specification, to form the first solid rings of the TBM's body. Once this foundational structure is in place, the single most important, most expensive, and most precise component of the entire machine is installed: the main bearing. This is a colossal ring of perfectly machined steel, a masterpiece of metallurgy that can be 10 meters in diameter and weigh hundreds of tons. It is the heart of the machine, the component that will allow the cutter head to rotate against the immense resistance of the rock while bearing the full forward thrust of the entire machine. Its installation is the most delicate and painstaking part of the entire assembly, a process that can take weeks, as it must be aligned with a degree of precision that is almost absolute, for any flaw in its placement would be magnified into a catastrophic failure once the machine begins to bore. With the heart of the Titan securely in place, the time comes to give the machine its face. The cutter head, the business end of the TBM, is often the last major component to be assembled on the surface, before being lowered into the pit. This massive steel disc, which has been custom designed for the specific geology of its journey, is laid out and its tools are installed. Dozens, sometimes hundreds of cutting instruments are meticulously bolted into place. These include heavy, hardened steel disc cutters, designed to create high-pressure point loads that crack and fracture solid rock, and softer tungsten carbide scrapers and plows, designed to scoop away softer ground like clay and sand. When this immense armored disc is fully dressed, it is lifted and carefully rotated into a vertical position. Then, in the most dramatic moment of the assembly, the entire multi-hundred-ton cutter head is lowered into the launch chamber and painstakingly bolted onto the main bearing. This is the moment of transformation. The collection of rings, motors, and hydraulic rams ceases to be a collection of parts and becomes a recognizable entity. A machine with a face, a purpose-built monster designed for a singular, relentless task to consume the earth. A tunnel boring machine, however, is far more than just a rotating drill bit. It is a dense, complex, and self-contained ecosystem. And now its internal organs must be installed. Deep within the protection of the main shield, a labyrinth of machinery is assembled, a ring of colossal electric motors, each the size of a small car, is installed and connected to the gearboxes that will drive the cutter head. The immense hydraulic power pack is put in place, a system of pumps and reservoirs that will power the rams that propel the machine forward, and the segment erector that builds the tunnel. The screw conveyor is installed, a massive Archimedes screw that sits directly behind the cutter head, designed to catch the excavated rock and soil, or muck, and transport it through the machine to the waiting disposal system. And at the center of it all, the operator's cabin is installed. This is the soundproof, air-conditioned nerve center of the entire vessel, a cockpit packed with a dizzying array of screens, joysticks, and control panels, from which a small crew of highly trained pilots will guide the thousands of tons of steel on its slow and blind journey through the planet. The true scale of the machine, however, only becomes apparent when its body is attached. Trailing behind the main shield is a long, articulated series of platforms and gantries, a mobile factory that can be over 100 meters long. This is the backup, or trailing gantry, and it is assembled piece by piece in the launch chamber behind the main shield. These gantries are the machine's life support system. They carry the massive electrical transformers that power the motors, the colossal ducts that supply fresh air to the crew and remove dust and fumes, and the complex grout plants that will mix and pump the material used to fill the gap behind the tunnel lining. Most importantly, the trailing gantries house the automated systems for building the tunnel itself. They carry a stockpile of the precast curved concrete segments that will form the permanent tunnel lining, and they are home to the segment erector, a powerful robotic arm that picks up these multi-ton segments and places them in a perfect ring inside the tail of the TBM shield. The colossal steel serpent now fills the entirety of its concrete birthplace, a machine of almost unbelievable length and complexity, fully assembled deep within the earth. The final stage of its preparation is to connect it to the outside world, to give it the power and the sustenance it needs to begin its journey. A massive high-voltage power cable, its umbilical cord, is connected to the transformers on the trailing gantry. The primary ventilation ducts are attached, and giant fans on the surface roar to life, pumping a steady supply of fresh, breathable air into the deep. A network of pipes is connected, some to bring in water for dust suppression and cooling, others to bring in the components for the grout, and most crucially, the slurry pipes that will form the machine's excretory system, carrying the thousands of tons of excavated muck away from the cutter head and back to a treatment plant on the surface. Every system is now checked and double-checked. The motors are tested, the hydraulic lines are pressurized, the thousands of sensors are calibrated. The Titan is now alive, humming with an immense and latent power, its great steel face pressed firmly against a specially constructed concrete wall at the far end of the launch box. It is a beast in a cage, coiled and ready. The Titan is assembled, its hundreds of disparate parts now fused into a single, colossal entity. It is tested, it is powered, it is alive. The crew is in the control cabin. The engineers on the surface are monitoring every system on their screens. The moment has come. But how does this machine, with its thousands of tons of dead weight and immense internal friction, actually begin to move? How does it take its first, crucial bite of the living earth, and what are the immense, complex, and perfectly coordinated processes that must all happen in absolute synchrony? From the spinning of the cutter head to the placement of the very first concrete ring, to ensure that this first, terrifying step on a journey of many kilometers is not its last. The years of silent investigation and the months of colossal construction have all led to this single monumental moment. Deep within the earth, in the quiet, brightly lit expanse of the launch cathedral, the fully assembled, multi-thousand-ton Titan lies dormant. It is a machine tested 1,000 times in simulation. Its every system checked and rechecked, yet it has not moved a single centimeter under its own power. In the operator's cabin, the crew is in place, their faces illuminated by the glow of dozens of screens displaying a torrent of data from thousands of sensors. On the surface, in the central control room, a team of engineers watches the same data, their voices a calm and steady murmur over the communication lines. An immense, almost unbearable amount of potential energy, both mechanical and financial, is coiled within this single machine, waiting for the command to be unleashed. The launch of a tunnel boring machine is not a sudden, violent event. It is a slow, controlled, and almost impossibly powerful awakening, a moment of profound tension where the combined hopes of the entire project are focused on a single, terrifying goal: the first shove. A machine of such colossal mass cannot simply will itself into motion. Its own immense weight, and the friction of its hundreds of moving parts, create a staggering inertia. Furthermore, for its very first push, there is no completed tunnel for it to brace against. To solve this problem, a massive temporary structure of pure resistance has been built in the launch box behind the TBM. This is the launch frame, or thrust frame, a monumental wall of heavily reinforced concrete and steel, engineered for the sole purpose of taking the full, unbridled force of the machine's initial propulsion. The process begins with the pressurization of the hydraulic system. Then, with a deep and resonant hum, the TBM's propulsion rams, a ring of dozens of enormous hydraulic cylinders located in the main body of the machine, begin to extend. They do not push against the tunnel ring that isn't there yet. They push backwards, against this immense thrust frame. With a force equivalent to the thrust of dozens of jumbo jets, the rams begin to move, and the entire 4,000-ton machine, with a deep and shuddering groan, inches forward, scraping along the specially prepared launch cradle on the floor of the cavern. As the machine's face makes its first firm contact with the concrete head wall at the far end of the launch chamber, the second part of the awakening occurs. The colossal electric motors, deep within the machine's body, spool up to life, drawing an immense surge of power from the city's grid, with a sound that is less a noise and more a vibration that can be felt in the bones. The main drive engages, and the great cutter head, the armored face of the Titan, begins to slowly, inexorably rotate. The steel disc cutters, each one capable of exerting hundreds of tons of pressure on a single point, begin to grind against the concrete wall, which shatters and pulverizes as intended. After breaking through this sacrificial barrier, the cutter head tastes the living earth for the very first time, depending on the ground conditions it was designed for. Its method of attack will differ. In the soft, saturated clays and sands common beneath many cities, the machine will operate as an earth pressure balance or EPB TBM. Here, the cutter head chamber is deliberately kept filled with the excavated soil, mixing it into a thick, toothpaste-like paste. The pressure of this paste is precisely controlled by the TBM operator, matching the pressure of the surrounding ground and water to the kilopascal, creating a state of perfect equilibrium that prevents the tunnel face from collapsing. The moment the machine begins to eat, its entire industrial ecosystem must spring to life in perfect synchrony. The excavated earth, the tons of rock, clay, and sand being shaved from the tunnel face every minute, cannot be allowed to accumulate. This material, known as muck, is immediately funneled from the cutter head chamber into the maw of the screw conveyor. This is a colossal Archimedes screw, housed in a heavy steel tube that rotates to transport the muck from the high-pressure environment at the front of the machine through its body and out onto a conveyor belt system at the back. This screw conveyor is not just a transport device. In an EPB machine, the speed of its rotation is one of the primary tools the operator uses to control the pressure in the cutter head chamber. From the screw conveyor, the muck is deposited onto a continuous, articulated conveyor belt that runs the entire length of the trailing gantries. At the very end of this long internal river, the muck is finally dropped into waiting carts on a small railway, or mixed into a slurry to be pumped, to begin its long journey back out of the tunnel and up to the surface for disposal. After the TBM has crept forward by the precise length of a single tunnel ring, a distance typically between 1.5 to 2 meters, the entire machine comes to a halt. The forward propulsion stops, the cutter head slows to a stop, and the conveyor belts fall silent. Now, the most critical and repetitive act of the entire tunneling process begins: the construction of the permanent tunnel. Deep within the tail of the TBM shield, the segment erector, a powerful and precise robotic arm, awakens. Guided by the operator, the erector's arm extends back to the trailing gantry, where the precast concrete tunnel segments are stored. It uses a powerful vacuum gripper, or a mechanical clamp, to pick up one of these multi-ton curved segments, which have been delivered to it by a smaller gantry crane. The erector arm then lifts, rotates, and swings the segment forward, placing it with millimeter accuracy against the inside of the TBM's steel tail shield. This process is repeated segment by segment, typically 5 or 6 main segments, and a final, smaller wedge-shaped keystone, which are all bolted together to form a perfect, solid, and waterproof concrete ring. With the first ring of the permanent tunnel now built deep inside the machine's protective shield, the magic of the TBM's locomotion can be revealed. The propulsion rams, which had been pushing against the temporary launch frame, now fully retract. The entire ring of rams is then repositioned and they extend again. But this time, they do not push backwards. They push forwards, their steel feet pressing directly and firmly against the face of the brand new, freshly installed concrete ring. The machine now uses the very tunnel that it is creating as the foundation for its own propulsion. This is the moment the fundamental boring cycle is born. The relentless and repetitive rhythm that will be the heartbeat of the project for the months and years to come. The cycle is simple in concept, but immensely complex in execution. Bore forward the length of one ring, stop, build a new ring inside the tail shield, retract the rams, reposition the rams against the new ring, and push forward again. It is a process of continuous, self-referential creation. A serpent crawling through the earth by perpetually building and pushing off of its own skin. However, there is one final, crucial, and invisible step that must happen in perfect concert with this cycle. As the TBM moves forward, it leaves a small empty gap, a void just a few centimeters wide, between the outside of the newly placed concrete ring and the slightly larger circle that was actually carved by the cutter head. This gap, known as the annulus, is incredibly dangerous. If left unfilled, it would allow the immense weight of the surrounding ground to slowly shift and settle, which could lead to subsidence on the surface and uneven pressures on the tunnel lining. To prevent this, as soon as a ring is built and the TBM has pushed off it, this void is immediately filled. Through small, precisely placed holes in the concrete segments, a specialized grout mixture is pumped under pressure. This grout, a fluid cement-like material, flows into the annulus, completely filling the void and hardening within a few hours. This critical act of annulus grouting locks the tunnel ring into place, ensures that it is perfectly and evenly supported by the surrounding ground, makes the entire structure completely watertight, and guarantees the long-term stability of the tunnel. The cycle is now fully established and has been tested in the living earth. Bore, build, push, grout, a slow, methodical, and relentless rhythm that consumes the earth in front and leaves a perfect, permanent structure behind. The subterranean serpent is now truly alive, crawling away from its concrete womb and beginning its long journey into the darkness. But this journey is not through a simple, uniform substance, and its path is not a straight line. The TBM is a blind behemoth, and its crew, locked deep within its windowless steel shell, must navigate it with a degree of accuracy that is almost supernatural. How do the pilots, with no external visibility, know exactly where they are to within the width of a coin? How do they steer this colossal machine through the subtle, pre-planned three-dimensional curves of the tunnel's path, dipping beneath riverbeds and weaving around the deep foundations of skyscrapers to ensure that they arrive at their destination many kilometers away with no more than a few millimeters of error? The great subterranean serpent is now alive, its rhythmic cycle of bore, build, and push established as the new heartbeat of the deep earth. But its journey is a blind one. Locked within its windowless steel shell, the crew has no landmarks, no sunlight, no stars to guide their path. Yet they are tasked with navigating this 4,000-ton leviathan through a solid, opaque medium with a degree of accuracy that is almost supernatural. The tunnel they are creating is not a simple, straight line. It is a complex, three-dimensional alignment, a gentle, invisible ribbon that must weave its way through an unseen world of geological faults, competing subway lines, and the deep foundations of the skyscrapers that define the city's skyline. The challenge is immense. It is akin to performing laser eye surgery on a patient who is buried under a mountain, where an error of a single fraction of a degree compounded over a journey of many kilometers, would result in the machine emerging hundreds of meters off course. The brute force of the machine must, therefore, be slave to a guidance system of the most profound and delicate precision. This journey of precision begins long before the TBM is assembled, in the calm digital realm of the design office. The tunnel's path, known as its alignment, is one of the most meticulously engineered aspects of the entire project. Using the comprehensive three-dimensional ground model created during the geotechnical investigation, a team of specialist engineers plots the tunnel's exact course. This is a complex, high-stakes balancing act. The path must be designed with long, sweeping curves, as a machine of this length cannot make sharp turns. It must maintain a precise and often constantly changing gradient, allowing for the gentle inclines and declines required for trains to operate efficiently or for water to flow by gravity. And most critically, it must maintain a legally mandated and structurally vital clearance from every known obstacle, from the deep piles of a suspension bridge to the path of a rival subway line. The final result of this work is a single, continuous, three-dimensional line, a digital thread running through the virtual model of the Earth. This alignment is the sacred text for the project, the absolute and unchangeable pathway that the TBM must follow with unwavering fidelity. For this digital path to have any meaning in the real world, it must be anchored to it. The entire navigation system is therefore built upon a foundation of absolute truth established on the surface. Before the project begins, a team of surveyors walks the streets of the city directly above the proposed tunnel route, undertaking a task of almost obsessive precision. They establish a surface survey control network, a series of small permanent brass markers that are drilled and fixed into sidewalks, building foundations, and bridge abutments. Using a combination of state-of-the-art GPS receivers that can determine a position on the globe to within a few millimeters, and robotic total stations that measure angles and distances with incredible accuracy, the surveyors create a high-precision fixed grid of known coordinates along the entire length of the tunnel's path. This network becomes the project's ultimate frame of reference. It is the real-world manifestation of the digital plan, a series of immovable anchors from which every single measurement, both on the surface and deep within the Earth, will be derived. The next great challenge is to transfer this absolute truth from the sunlit world of the city streets down into the dark, isolated world of the tunnel. This critical process, known as traversing the shaft, is one of the most difficult and skill-intensive tasks in all of tunnel surveying. The survey crew must transfer the coordinates of the surface control points down the immense vertical drop of the launch shaft with almost no loss of accuracy. They achieve this using a combination of techniques, often employing highly precise optical plummets or vertical lasers to project a perfectly straight line of sight from a known point at the top of the shaft to a new point being established on the floor of the launch chamber below. This process is fraught with potential errors. The subtle movement of the air within the shaft, caused by temperature differences and ventilation systems, can bend the path of a laser beam. The slightest vibration in the surrounding ground can disturb the instruments. The surveyors must account for all of this, taking dozens of repeated measurements and using complex mathematical adjustments to establish a new set of control points deep in the Earth that are a true and perfect reflection of the network on the surface. Once this control network is established within the tunnel's starting chamber, the machine itself can be given its own set of eyes. Mounted deep within the forward section of the TBM's shield is its primary guidance system, a sophisticated laser-based instrument known as an automatic tail shield laser system. At its heart is a robotic total station, a device that can automatically track and measure distances and angles with incredible speed and accuracy. This total station is aimed not forwards, but backwards, into the tunnel that has already been built. As the TBM moves, the total station continuously and automatically locks onto a series of reflective prism targets, which have been mounted at precise locations on the newly installed concrete tunnel rings. The system's onboard computer knows the intended coordinates of these targets. By constantly measuring the current angles and distances to these known fixed points behind it, the software can perform a real-time calculation, a complex geometric triangulation, to determine the exact three-dimensional position and orientation, its pitch, roll, and yaw of the TBM at that very moment. This system is often supplemented by a series of inclinometers to measure tilt and, in some cases, a highly accurate gyro compass, which provides an independent continuous reading of the machine's heading, acting as a vital cross-check on the primary laser system. For the TBM pilot, locked in the control cabin, this torrent of complex geometrical data is distilled into a single, intuitive, and graphical display on their primary navigation screen. They do not see the rock and clay ahead of them. They see a virtual representation of their journey. The screen will typically show a cross-section of the tunnel, with a circle representing the current, real-time position of the TBM's cutter head, and a second target icon representing the intended design position according to the digital alignment. The difference between these two, the machine's deviation from the true path, is displayed numerically, in millimeters, for both the horizontal and vertical planes. The screen also shows the machine's roll angle, which is critical for ensuring the keystone of each ring is placed correctly at the top, as well as its pitch, showing if it is climbing or diving at the correct angle. The pilot's entire world, their entire sense of place and direction, is mediated through this single screen. Their job is to interpret this data and make the constant subtle adjustments required to keep the two circles, the real and the ideal, perfectly overlapped. Knowing where you are is one thing. Steering a 4,000-ton, 150-meter-long articulated cylinder through solid rock is another. The steering of a TBM is a slow, deliberate, and powerful art form, managed entirely through the machine's propulsion system. The ring of hydraulic rams that pushes the machine forward can be controlled with remarkable subtlety. The operator can choose to extend the rams on one side of the machine with slightly more pressure, or for a slightly longer duration than the rams on the other side. To make a gentle turn to the right, for example, the operator will apply slightly more thrust from the rams on the left side of the machine during a push cycle. This differential thrust causes the entire TBM to pivot, almost imperceptibly around its central axis. The machine is also often articulated, with a flexible joint behind the main shield, which allows it to make these slow, sweeping turns more easily. Steering is not an immediate action, but a process of anticipation. The pilot must constantly make tiny corrections, judging how the machine will react to the changing geology ahead, to ensure that it remains perfectly on the invisible line of the digital alignment. This highly automated and sophisticated guidance system is not left to operate on its own. The entire process is constantly verified and recalibrated by the human tunnel survey crew. The machine's navigation system is only as good as the known points it is measuring from. Therefore, after every 10 to 15 rings are installed, the boring process is paused and the survey team enters the newly built section of tunnel. They carry their own total station, which they set up on the last known, verified control point. They then perform a new set of measurements to precisely determine the coordinates of the prism targets on the most recently installed rings, and to establish a new forward control point. This process provides a regular, independent, and highly accurate check on the machine's onboard system, correcting for any tiny cumulative errors that may have crept in. It is a vital partnership between the relentless, automated precision of the machine's brain and the meticulous, methodical, and irreplaceable expertise of the human surveyor. With its path thus illuminated by an invisible and ever-extending web of lasers, and its position in the world known with a certainty that borders on the absolute, the TBM continues its relentless guided crawl through the deep earth. Ring by ring, meter by meter, the tunnel extends behind it, a perfect tube of concrete, a monument to a seamless fusion of colossal brute force and the most delicate and precise navigation. But every journey, no matter how long, must eventually come to an end. What happens when this meticulously planned voyage is over? What is the final act for our subterranean Titan when it finally senses, through the last few meters of rock and clay, the approach of its destination? The breakthrough, the moment the TBM's cutter head emerges into the light and air of a reception shaft, is a moment of immense celebration and relief. But it also marks the beginning of the end for the machine itself. How do you decommission and remove a colossal machine that is now many kilometers from its entry point, buried deep beneath a city? A machine whose entire purpose was to travel in one direction only. The journey's end is not a gradual arrival, but a final, violent confrontation with a man-made barrier. For months, or even years, the tunnel-boring machine has crawled through the natural geology of the Earth, its cutter head designed and armed for the specific rock and clay of its path. But its destination, the reception shaft, is a fortress of concrete and steel, identical to the one from which it was launched. The final few meters of the drive are therefore a slow, tense, and carefully calculated approach towards this final wall. In the control cabin, the atmosphere is electric. The pilots monitor the guidance system with an almost supernatural focus, making the last infinitesimal steering corrections to ensure the machine is perfectly aligned for its final act. The sound of the excavation changes, the deep grinding of rock giving way to the high-pitched scream of steel on reinforced concrete. For the engineers waiting in the reception shaft, it is a moment of profound anticipation, a vigil held in a deep, silent, concrete cavern, as they wait for the arrival of the beast they sent away on its long journey, so long ago. The breakthrough is a moment of pure, unadulterated engineering theater. It begins not with a roar, but with a series of quiet, ominous creaks and groans from the far wall of the reception shaft. A fine web of hairline cracks appears on the concrete surface, spreading outwards from a central point, a puff of dust, a trickle of water. Then, with a sudden sharp crack, the tip of a single, hardened steel disc cutter punches through the wall, a glint of metal in the dark concrete. It is the first sign of life. This single breach is quickly followed by others, as the immense, rotating power of the cutter head overmatches the strength of the wall. With a deafening roar and a cascade of shattered concrete and twisted steel rebar, a section of the wall gives way, and the monstrous, muck-covered face of the Titan emerges from the darkness of its own creation into the bright, electric light of the reception shaft. As the entire cutter head slowly, inexorably pushes its way into the open air, a wave of triumphant shouts echoes through the cavern. It is a moment of catharsis, a celebration not just of the journey's end, but of the perfect, flawless execution of a plan that was years in the making. But the machine's work is not quite finished. The cutter head may be in the reception shaft, but the vast majority of its 150-meter-long body is still in the tunnel. The final push must be completed. With the resistance of the Earth now gone, the TBM performs its last careful shoves, driving its entire main shield, the full length of its forward body, completely into the open space of the cavern. It is now a beast that has fully emerged from its lair. The crew can now perform the final act of the boring cycle, the construction of the last permanent tunnel ring. This is often a more complex and specialized task, as this ring must form a perfect watertight seal with the wall of the reception shaft. a critical connection that is often reinforced with a special collar of steel and grout. With this final ring in place, the primary purpose for which this multi-million-dollar machine was designed and built is now complete. The tunnel is bored. The path is made. Now begins the somber and laborious process of the Titan's autopsy. The colossal machine, an instrument of relentless forward motion, cannot be backed out of the tunnel it has created. It must be taken apart piece by piece and removed from the deep. A new team of workers, specialists in decommissioning, descends upon the now silent and powerless machine, with cutting torches that throw brilliant showers of sparks through the cavern. They begin to systematically dismember the great steel beast. The cutter head, the heroic face of the machine, is unbolted from the main bearing and cut into smaller, more manageable sections. The massive curved plates of the main shield are sliced apart. The colossal main bearing, the motors, the gearboxes, and the hydraulic power packs are all disconnected and carefully prepared for their final journey to the surface. It is a slow, loud, and almost brutal process, a strange reversal of the meticulous assembly we witnessed in the launch shaft. It is the deconstruction of a hero, a necessary and unglamorous end for a machine that has fulfilled its singular destiny. The pieces of the fallen giant are then removed from the deep, one by the cranes waiting at the top of the reception shaft. Their fates will vary. The main shield and the trailing gantries, the basic steel skeleton of the machine, are typically sold for their weight in scrap metal, destined to be melted down and reborn as something new. But the most valuable and complex components, the heart and brain of the machine, are often salvaged. The main bearing, the primary drive motors, and the sophisticated electronic guidance systems are so expensive and so specialized that they are often shipped back to the manufacturer's factory. There, they will be completely refurbished, upgraded, and held in inventory, waiting to become the core of a new TBM, a new Titan to be sent on a different journey beneath a different city. In some high-profile projects, the cutter head, the most iconic part of the machine, is saved. It may be painstakingly restored and placed on public display near the entrance of the new tunnel, a permanent, silent monument to the great journey that was completed and the magnificent machine that made it possible. With the TBM now gone, the tunnel it has left behind is a vast, empty, and raw concrete tube. It is a structurally complete space, but it is not yet a functioning piece of infrastructure. The process of finishing the tunnel now begins, a phase of construction that can take even longer than the initial boring. For many types of tunnels, especially those designed to carry water or to exist in environments with very high water pressure, the first step is the installation of a second, inner skin. A waterproof PVC membrane is meticulously applied to the inside of the precast concrete rings, creating an impermeable barrier. Then, a second, inner layer of concrete is cast in place, poured and smoothed to create a final, seamless, and completely waterproof tube. This tunnel within a tunnel design provides a 100-year lifespan and a level of redundant safety required for the most critical pieces of urban infrastructure, ensuring the passage will remain dry and stable for generations to come. The empty tube must then be given its organs, its nervous system, and its purpose. This is the final and most complex phase of the construction. For a subway tunnel, this involves the painstaking installation of the track bed, the laying of thousands of tons of ballast, concrete sleepers, and the two parallel ribbons of steel rail, all set to a precise and unforgiving geometry. For a road tunnel, this is when the road surface itself is paved, the curbs are installed, and the lane markings are painted. Then comes the vast and intricate web of mechanical and electrical systems. Thousands of kilometers of high voltage cables are run to power the lighting, the signaling systems, and the ventilation fans. The ventilation system itself, with its colossal jet fans mounted to the tunnel ceiling, is installed to manage the flow of air and the exhaust from vehicles. And finally, the critical life safety systems are put in place. The emergency walkways, the fire suppression pipelines, the communication systems, and the thousands of sensors that will monitor the tunnel's health for its entire operational life. The single-bore tunnel, a perfect and pristine cylinder carved by a titan of steel and guided by an invisible web of lasers, is now a complete and functioning masterpiece of modern engineering. It is a testament to a process that is both brutally powerful and exquisitely precise. But the needs of a modern city are often more complex than a simple, linear path. What happens when the challenge is not a single long passage, but a vast, interconnected, multi-level subterranean hub? How do engineers move beyond the one-dimensional march of the TBM to create the immense, complex, and architecturally ambitious caverns required for a major downtown subway station? This requires a completely different philosophy, a method that involves not a relentless advance, but the delicate, sequential, and almost sculptural art of shaping a void from within. This is the world of controlled explosions, of sequential excavation, and of a technique that listens to the earth as it works. The new Austrian tunneling method. The tunnel boring machine is the undisputed master of the linear path, a titan of engineering designed to create a perfect, continuous, and uniform cylinder with relentless efficiency. Its entire being is optimized for a singular purpose: to advance. But the modern metropolis requires more than just simple arteries. It demands the creation of vast, complex, and often architecturally ambitious subterranean spaces. The downtown subway station, a multi-level cavern with intersecting passageways, escalator shafts, and soaring open atriums, presents a challenge that the one-dimensional march of the TBM is utterly unsuited for. To create such a bespoke, non-uniform void in the heart of the earth requires a profound shift in philosophy. One must move away from the mindset of a driller and adopt the mindset of a sculptor. This requires a method that is not about overpowering the ground with a steel shield, but about working in delicate and harmonious partnership with it. It is a method of observation, of patience, and of sequential controlled creation. This is the world of the new Austrian tunneling method. The core philosophy of this method, often referred to as ANETM, is a beautiful and deeply counterintuitive principle that revolutionized modern tunneling. For centuries, the conventional wisdom of digging in soft ground was to fight the immense pressure of the earth with brute force, using heavy, rigid, and expensive supports like cast iron or thick steel beams to hold the ground back. The new Austrian tunneling method, developed in the mid-20th century, turned this entire philosophy on its head. Its creators observed that when a void is excavated, the surrounding rock and soil, in the process of trying to move into that void, naturally redistributes its stress and forms a compressed, self-supporting arch around the opening. The native ground itself, if allowed to deform in a controlled and limited way, actually wants to hold itself up. The genius of NatIm is that it is designed to mobilize this inherent strength of the rock mass. The initial support system is not rigid, it is deliberately flexible, designed to work in concert with the ground, turning the very rock and soil that was once seen as a dangerous liability into the primary structural component of the tunnel itself. The practical application of this philosophy is a slow, cyclical, and almost sculptural process. A vast cavern is never excavated all at once. It is revealed in a careful and predetermined sequence of smaller excavations. The process typically begins at the very top, or the crown of the future cavern, with the excavation of what is known as the top heading. In softer ground, this is done with a road header, a powerful excavating machine with a large rotating cutting head, studded with tungsten carbide picks, which selectively grinds away the earth. In hard rock, this is achieved through the precise and controlled use of explosives, a technique known as drill and blast, where a carefully calculated pattern of charges is used to break up a limited section of the rock face. The key to this first step is that only a small, manageable portion of the tunnel face is excavated at a time, typically for a length of only a single meter. This minimizes the area of unsupported ground, ensuring the natural stability of the rock arch is never compromised. Immediately following this initial cut, and this is the most critical and time-sensitive step in the entire cycle, the newly exposed earth is given an artificial skin, before the ground has a chance to unravel or deform uncontrollably. A thin layer of a special, fast-setting, and high-strength concrete mixture called shotcrete is applied. This is not concrete that is poured into forms. It is a dry or wet mix that is propelled at high velocity from a nozzle, directly onto the raw, contoured surface of the newly excavated rock and soil. This process, often carried out by a skilled operator guiding a robotic spraying arm, creates a thin, flexible, but remarkably strong initial lining that conforms perfectly to every nook and cranny of the excavation. This shotcrete skin is the primary tool of the Natiem philosophy. It is strong enough to prevent the surface from crumbling, but flexible enough to allow for the small, controlled amount of deformation that is necessary for the ground to mobilize its own inherent arching strength. This thin, sprayed concrete skin, however, is not sufficient on its own to support the immense geological loads. It must be integrated with the surrounding rock mass, turning them into a single composite structure. This is achieved by installing a systematic pattern of rock bolts. These are long steel rods, ranging from 3 to 12 meters in length, which are drilled deep into the rock strata surrounding the tunnel's profile. Once inserted, these bolts are either grouted into place or mechanically expanded at their far end, and then tensioned. These bolts act like immense surgical stitches, clamping the various layers and blocks of rock together, preventing them from shifting or sliding and effectively mobilizing a huge volume of the native rock to participate in supporting the opening. In addition to the bolts, curved, lightweight steel frames known as lattice girders are often embedded within the first layer of shotcrete. These do not provide the primary support, but they give the shotcrete layer its precise geometric shape and provide a safe, initial reinforcement for the workers before the concrete has fully cured. With the crown of the tunnel now securely excavated and supported, the sculptural process continues downwards. The next step is to excavate the middle portion of the cavern on either side, a section known as the bench, just like the top heading. This is done in a slow and sequential manner, advancing only a short distance at a time, and just as before, each new section of excavated ground is immediately supported with a new layer of shotcrete and a further pattern of rock bolts, which are carefully integrated with the support system already in place above. Once the bench is complete, the final section of the profile, the floor of the tunnel, known as the invert, is excavated and secured in the same methodical fashion. This cyclical process, excavate a little, supported immediately, excavate a little more, supported immediately, is the fundamental rhythm of the method. It is a slow, patient, and cautious dance with the earth, a process of gradually revealing and securing the final shape of the vast cavern from the top down. At the very heart of the Natiem philosophy is the principle of observation. The tunnel is not built according to a rigid, predetermined set of plans. It is built in response to the real-time behavior of the ground itself. To achieve this, the newly excavated cavern is turned into a highly monitored scientific instrument. A vast array of geotechnical instrumentation is installed as the work progresses. Extensometers are placed in boreholes to measure, with microscopic accuracy, how much the different layers of rock are moving. Pressure cells are embedded in the shotcrete lining to measure the buildup of stress and load, and convergence bolts are installed across the tunnel, with their distance from each other being measured constantly by surveyors to determine how the cavern is deforming as a whole. The data from these thousands of sensors is fed back to the engineering office on the surface and monitored 24 hours a day. This constant stream of information allows the engineers to listen to the ground to understand if it is behaving as their models predicted. If the ground is showing more stress or movement than expected, the support system can be adapted on the fly. The next layer of shotcrete can be made thicker, or the pattern of rock bolts can be made denser. This makes NAT2 a living, adaptive method, a true partnership between the engineer and the geology. Only after the entire cavern has been fully excavated and the primary lining of shotcrete and rock bolts is deemed to be completely stable does the final stage of construction begin. The primary lining, though structurally sound, is a rough, uneven surface, and it is not designed to be perfectly waterproof. To create the final permanent structure, a comprehensive waterproofing membrane is meticulously installed. This is a thick, durable, and flexible skin of a material like PVC, which is carefully welded and sealed to cover every square meter of the cavern's interior, creating an impermeable barrier that will prevent any groundwater from ever entering the station. Once this membrane is in place, the final, reinforced concrete inner lining is constructed. This is the thick, smooth, and often architecturally expressive concrete shell that the public will ultimately see. This final lining is not just for aesthetics. It is the permanent, structural heart of the cavern, designed to be completely watertight and to bear the loads of the earth for well over a century. The Great Sculpted Cavern, a bespoke space born from a harmonious and observational dance with the earth, is now complete. The new Austrian tunneling method has allowed engineers to create a complex, multi-level void, a feat of subterranean architecture that the relentless cylindrical march of the TBM could never hope to achieve. But these two great philosophies of tunneling, the brute force shielded advance of the TBM and the delicate adaptive approach of NITM, are not always mutually exclusive, and neither can function without confronting one of the oldest, most powerful, and most unpredictable enemies of the deep earth, water. What happens then, when the path of a tunnel must pass not just through damp soil, but directly beneath a massive flowing river, or even the open sea? How do we build dry, stable passages on the bed of a harbor, fighting against colossal hydrostatic pressures that threaten to crush, breach, and flood any structure in an instant? This requires moving beyond boring and sculpting into a world where tunnels are not dug but are built on the surface, and then deliberately and precisely sunk. We have witnessed the relentless, forward-boring march of the shielded Titan, and the patient, sculptural craft of the observational method. Both are philosophies designed to conquer the solid earth, but we now arrive at a challenge of a different order of magnitude, an adversary that cannot be simply drilled through or sculpted away, a wide, deep, and powerful body of water. When the path of a tunnel must cross a major river, a busy harbor, or a coastal strait, the geology of the seabed is often a treacherous mixture of soft, unconsolidated silts, muds, and waterlogged sands, often extending to immense depths. To drive a conventional TBM through such ground would be a perilous and astronomically expensive undertaking, fighting a constant high-pressure battle against mud and water. To solve this seemingly insurmountable problem, engineers devised a solution of breathtaking audacity and lateral thinking. They conceived of a method that does not bore through the ground at all. Instead, it is a hybrid of naval architecture and heavy civil engineering, a method where the tunnel is not dug but is built, floated, and then deliberately and with immense precision sunk. This is the world of the immersed tube tunnel. The life of an immersed tube tunnel begins not in the water, but in a vast, purpose-built factory on dry land. This is the casting basin, or dry dock, an immense construction site, often located many kilometers from the tunnel's final destination, where the individual elements of the tunnel are forged. These are not small pieces. A single tunnel segment can be over 100 meters long, 30 or 40 meters wide, and 10 meters high, a colossal hollow box of heavily reinforced concrete or dual-walled steel, weighing as much as 50 or 60,000 tons. Inside this dry dock, a factory-like assembly line is established to construct these behemoths. Immense movable formworks are erected, and a complex web of steel reinforcement is meticulously tied into place. Then, in a series of massive continuous pours, thousands of cubic meters of high-strength concrete are cast to form the segment's floor, walls, and roof. At each end of these colossal concrete boxes, a critical feature is installed: a massive compressible rubber seal, known as a Gina gasket, and a temporary but immensely strong steel bulkhead that will, for a time, turn this piece of a tunnel into a seaworthy vessel. When a series of these colossal segments is fully constructed and cured, the most dramatic and counterintuitive phase of their creation begins: the dry dock. A workplace that has been a hive of terrestrial construction activity for many months is prepared to be flooded. The massive sea gates that separate the casting basin from the adjacent river or harbor are sealed, and immense pumps are slowly switched on, filling the basin with millions of gallons of water. With agonizing slowness, the water level begins to rise. And then, a moment of quiet and profound engineering magic occurs. These colossal 50,000-ton objects, these structures made of the very essence of rock and steel, begin to lift from their foundations, their hollow, watertight design sealed by the temporary steel bulkheads, allows them to become buoyant. The tunnel segments, each as massive as a naval destroyer, are now floating, transformed from static structures into immense rectangular and strangely graceful vessels, waiting in their temporary lagoon for the next stage of their journey. That journey is a slow and majestic procession, a carefully choreographed naval operation. A flotilla of powerful tugboats enters the now flooded dry dock and is carefully secured to a single floating tunnel segment. Then, the sea gates are opened and the segment is gently nudged out into the open waterway. The process of towing this immense, unwieldy, and almost shapeless object to the final tunnel site is a painstaking exercise in navigation and seamanship. The segment has a huge surface area, making it vulnerable to winds, tides, and river currents. The tugboat captains must work in perfect concert, their movements guided by a central command and a constant stream of data from GPS positioning systems and weather reports. For the people on the shore, it is a bizarre and stunning spectacle. A massive, featureless block of what appears to be a sunken building, floating serenely on the surface of the water, on a journey to its final, invisible resting place. While the tunnel segments are being fabricated and transported, a parallel and equally massive operation is taking place at the bottom of the river. A fleet of specialized dredging vessels begins the task of preparing the tunnel's bed. These are often powerful cutter suction dredgers, which use a rotating saw-like head to break up the silts and clays of the riverbed, and a powerful centrifugal pump to suck the material up and pipe it away. Following the precise, predetermined alignment of the tunnel, these machines excavate a wide and deep trench in the river floor. This trench must be perfectly graded and shaped to accommodate the tunnel segments. Once the trench is excavated, a final, critical layer of preparation begins. A specialized vessel, known as a fall pipe vessel, moves over the trench, using a long, articulated pipe guided by GPS and sonar. It deposits a perfectly smooth and level foundation course of crushed gravel or stone at the bottom of the dredge channel. This gravel bed is the foundation upon which the entire tunnel will rest, and its placement must be accurate to within a few centimeters. With the trench prepared and a tunnel segment now floating and moored in position above it, the single most tense and critical moment of the entire process arrives: the controlled sinking. The segment is maneuvered into a large floating steel structure known as a sinking rig, which is anchored with immense precision directly over the trench. The process of descent begins by slowly pumping thousands of tons of water into large ballast tanks that were cast into the segment's concrete structure. As the weight of this ballast water overcomes the segment's natural buoyancy, it begins to sink. This is not a free fall. The segment is connected by a series of powerful computer-controlled winches and cables to the sinking rig above, allowing its descent to be controlled with millimeter-per-second precision. Its exact position in three-dimensional space is monitored in real time by a combination of differential GPS and acoustic transponders on the seabed. For the final approach, a team of divers, or, more commonly, a remotely operated vehicle, ROV with powerful lights and cameras, is sent down to provide the final visual confirmation, guiding the colossal structure onto its gravel bed with the delicacy of a feather. The moment of connection is an act of sheer brute force elegance. The new segment is carefully guided by the winches and its own ballasting system until its steel bulkhead makes contact with the bulkhead of the segment that was previously laid at the bottom of the trench. Now the genius of the system is revealed. A series of powerful hydraulic rams on the new segment may push it firmly against the old one. Then a pump is activated which removes all the water from the small cofferdam-like space between the two steel bulkheads. As this water is removed, a colossal and invisible force is brought to bear. The full hydrostatic pressure of the river or sea above, a force of thousands of tons, now pushes on the back of the new segment, driving it forward with immense power. This force compresses the massive rubber Gina gasket with such intensity that it creates a perfect, immediate, and incredibly durable waterproof seal. The two segments are now one, joined by the invisible hand of the water's own immense weight. The tunnel is now a series of connected watertight boxes, resting in a trench on the riverbed, but it is not yet a permanent part of the landscape. The final major step is to lock it into place by backfilling the trench. A different kind of vessel now comes to the site, one designed to carefully place material back onto the riverbed. A layer of sand is often placed first, filling the gaps beneath the curved bottom of the tunnel and its flat gravel bed, ensuring it is perfectly supported. Then the main backfill material, often the originally dredged material or new rock and sand, is carefully placed back into the trench, covering the sides and the top of the tunnel segments until the entire structure is completely buried. This protective layer of backfill serves two crucial purposes. It provides the final immense weight that locks the tunnel firmly in place and prevents it from moving, and it protects the structure from any potential future damage, such as from a ship's anchor or the scouring action of the river's currents, effectively restoring the riverbed to its original state. The impossible has now been achieved. A dry, stable, and continuous passage, a tunnel that was built in a factory on dry land, now rests securely at the bottom of a river, a testament to a brilliant fusion of heavy construction and precise naval architecture. But all of these methods that we have explored, the relentless advance of the TBM, the sculptural dance of NATM, and the sunken segments of the immersed tube, share a common vulnerability. They are all, by their nature, long, linear, and relatively rigid structures, created by humanity and imposed upon a world that is not static. The Earth itself moves. Tectonic plates grind against one another. The ground trembles, and our great cities are sometimes shaken by the immense and unpredictable violence of an earthquake. How then do you design and build a tunnel, a structure that is by its very nature confined and brittle, to survive and remain safe in the heart of a seismic zone? How do you engineer a passage that can bend, flex, and absorb the colossal energy of the planet when the very ground it is built within is trying to tear itself apart? We have explored the creation of tunnels through the varied and often treacherous geology of the Earth, but we have done so under the assumption that the ground itself is a stable and stationary medium. This is a luxury that engineers in many of the world's most populated regions do not have. They must build their subterranean arteries in the heart of seismic zones, in places where the very planet is alive and capable of unleashing almost unimaginable violence with little or no warning. This presents a profound and terrifying challenge. A tunnel is, by its very nature, a long, linear, and relatively brittle structure, locked into the surrounding Earth. What happens to this rigid tube when the Earth it is locked into is suddenly subjected to the violent shearing and compressive waves of a major earthquake? The intuitive answer is catastrophic failure. But the truth is far more complex, and it reveals a surprising and paradoxical resilience that engineers have learned to harness through an array of ingenious and counterintuitive designs. The key to this paradox lies in understanding how a buried structure behaves differently from one on the surface. A skyscraper, an antenna, or a bridge, when struck by the seismic waves of an earthquake, is subjected to immense inertial forces. The ground moves violently beneath it, but the structure's own mass, its inertia, resists this movement, causing it to whip back and forth with destructive intensity. A tunnel, however, being completely encased by the ground, has very little freedom to move independently. It is, for the most part, forced to move in concert with the surrounding rock and soil. This phenomenon, known as kinematic interaction, means that the primary stress on a tunnel during an earthquake is not from violent shaking, but from the strain of the ground itself deforming around it. The tunnel is stretched, squeezed, and bent along with the Earth. Therefore, the primary goal of seismic tunnel design is not to create a structure of infinite strength to resist the shaking, but to create one of exceptional toughness and flexibility to survive the stretching. The real dangers to a tunnel in an earthquake, then, are not what one might first imagine. The most catastrophic failures are typically caused not by the seismic waves themselves, but by the ground failures that these waves can trigger. In areas with soft, water-saturated sandy soils, the intense shaking can cause a terrifying phenomenon known as liquefaction. The soil instantaneously loses all of its strength and begins to behave like a dense fluid. A tunnel, being a hollow and relatively buoyant structure, can be forced to float upwards through this liquefied ground, breaking apart and rising to the surface. The single most severe and almost indefensible threat is direct fault displacement, where a tunnel happens to cross an active fault line that ruptures, causing the two sides of the tunnel to be sheared apart by several meters in an instant. At the tunnel's portals, the entrances and exits, the shaking can trigger immense landslides on the surrounding hillsides, burying the openings under thousands of tons of rock and soil. And where a tunnel passes from a section of solid bedrock into a section of soft soil, the two materials will respond to the seismic waves very differently, creating immense stress and a potential shearing point at this geological boundary. The first and most fundamental line of defense against these forces is built directly into the tunnel's primary lining, into the very DNA of its concrete and steel. The key engineering principle is ductility, the ability of a material to deform and stretch under extreme stress without suffering a brittle failure. The goal is to create a lining that can bend and absorb an immense amount of energy before it breaks. This is achieved through the meticulous design of the steel reinforcement within the concrete. In seismic zones, engineers will specify the use of special, high ductility steel rebar which is designed to yield and stretch significantly, acting like a tough internal webbing that holds the concrete together even after it has cracked. In recent decades, this has been augmented by the use of steel fiber reinforced concrete. In this method, thousands of tiny hair-like steel fibers are mixed directly into the concrete, creating a composite material with incredible toughness. These microscopic fibers act as a three-dimensional net, bridging any cracks that form and preventing them from propagating, thus allowing the structure to absorb the earthquake's energy without shattering. For the modern TBM bored tunnel, which is constructed from a series of precast concrete rings, the most vulnerable points are the joints between these segments. A long tube made of hundreds of individual rigid rings is only as strong as the connections between them. To solve this, engineers have developed seismically resilient segmental joints that transform this potential weakness into a source of strength. Instead of being rigidly bolted together, the segments are designed to be flexible. They are connected with specialized, highly compressible gaskets, and the concrete rings themselves are sometimes designed with articulated or knuckle joints. These allow each individual ring to rotate and shift slightly in relation to its neighbors. During an earthquake, as a seismic wave passes through the ground, this segmental lining can flex and move along with it, with the deformation being distributed across hundreds of these flexible joints. The entire tunnel behaves less like a rigid, brittle pipe, and more like the spine of a serpent, its overall flexibility derived from the small controlled movements of its individual vertebrae. The ultimate challenge, however, is when a tunnel has no choice but to cross a known and active geological fault line. This is a problem that cannot be solved by simple flexibility. It requires a solution of profound ingenuity and planned sacrifice. For these critical crossings, engineers will design and build a special, sacrificial section of the tunnel. This often takes the form of a much larger, oversized concrete box or cavern that is constructed around the tunnel at the precise point of the fault. Inside this cavern, the tunnel itself is not a continuous, rigid tube. Instead, it is designed as a series of nested, sliding steel collars, like the sections of a telescope, or as a highly flexible, bellows-like structure capable of compressing, extending, and shearing by several meters without breaking its internal seal. This entire flexible joint is then often packed in a soft, crushable, and energy-absorbing material. The entire design is a pre-planned point of failure. When the earthquake strikes and the fault ruptures, this special section is designed to be destroyed, absorbing the immense shearing movement of the earth and sacrificing itself to protect the integrity of the main tunnel on either side from a catastrophic breach. Immersed tube tunnels, resting in the soft silts of a riverbed, require their own unique set of seismic solutions to prevent them from being torn apart by the differential movement of the ground. The primary tool here is base isolation, a principle that seeks to decouple the structure from the most violent motions of the earth. This is achieved by making the connections between the massive sunken tube segments flexible. These joints are often sealed with colossal, specially designed rubber elements, sometimes called gaskets or seismic joints, which are capable of safely accommodating large deformations, allowing the segments to move independently without losing their watertight seal. The critical connection between the end of the immersed tube section and the land-based approach structures is another point of extreme vulnerability. These junctions are often designed with massive sliding bearings and flexible seals, creating a sort of structural fuse that allows the two distinct parts of the tunnel to move independently by several feet, ensuring that the powerful shaking of the land-based structure is not violently transferred to the more fragile tube resting in the soft riverbed soils. The final layer of protection in the modern seismic tunnel is not structural, but informational. In many seismically active regions, tunnels are now integrated into sophisticated earthquake early warning systems. These systems rely on a wide network of seismometers that can detect the first non-destructive energy waves that travel outwards from an earthquake's epicenter, known as P waves. These P waves travel much faster than the more destructive shearing S waves. This provides a precious warning, ranging from a few seconds to over a minute, depending on the distance from the epicenter. All trains within the tunnel can be automatically brought to a controlled stop. All entrance portals can be closed to traffic with lighted barriers. The ventilation systems can switch to their maximum emergency mode, and an alert can be sent to local emergency services. This transforms the tunnel from a passive structure that must simply endure the earthquake into an active and intelligent system that can sense the danger coming and take steps to protect the lives of those within it. By embracing the principle of flexibility over rigidity, by meticulously designing for ductility, and by creating ingenious sacrificial limbs to protect the heart of the structure, engineers can now build subterranean passages that can withstand the most violent and convulsive outbursts of the planet itself. The tunnel has evolved from an isolated object into a complex system, a structure that is deeply integrated with the very geology and seismology of its location. But tunnels face threats that are not only from the natural world outside, but from the very purpose for which they are built, and the traffic that they carry. Of all the operational dangers that a tunnel faces in its daily life, the most terrifying and the most challenging from an engineering perspective is a catastrophic fire. How do you manage the unique and terrifying physics of a fire in a long, enclosed tube? How do you control the rapid spread of smoke, evacuate potentially thousands of people, and give firefighters a chance to battle a blaze in one of the most hostile and dangerous environments imaginable? Having been designed and constructed to withstand the immense and violent convulsions of the planet itself, the modern tunnel must now face a threat that is not external, but internal. It is a danger born from the very traffic and purpose for which it was built. Of all the operational hazards a tunnel faces in its long life, none is more feared, nor more furiously engineered against, than a catastrophic fire. A fire in a long, enclosed and linear tube is a fundamentally different and far more terrifying beast than a fire in the open air. The confined geometry of the tunnel acts like the barrel of a cannon, transforming a simple vehicle fire into a fast-moving, superheated, and toxic inferno. The heat, unable to dissipate into the open sky, is channeled along the tunnel's ceiling, creating a rapidly advancing layer of superheated gas that can reach temperatures of over 1,000 degrees Celsius. This radiant heat can cause every combustible material for hundreds of meters ahead of the fire to spontaneously ignite, and the smoke, thick with carbon monoxide and other deadly poisons, is channeled by the tunnel's shape into a dense, blinding, and suffocating plug that can travel faster than a person can run, quickly overwhelming the entire space. In a tunnel fire, it is almost never the flames that kill. It is the smoke, and the battle for survival is a battle to control the air itself. The first and most critical line of defense in this battle is a multi-layered system of prevention and intelligent, instantaneous detection. The best way to survive a tunnel fire is to prevent it from ever taking hold. This philosophy begins with the very materials of the tunnel's interior. Every component, from the insulation on the thousands of kilometers of electrical wiring to the wall cladding and signage, is legally required to be manufactured from special, low-smoke, zero-halogen, and fire-retardant materials. But should a fire start, typically from a vehicle accident or mechanical failure, the goal is to detect it in its absolute infancy. This is achieved with a sophisticated and redundant web of electronic sensors. Along the ceiling of the tunnel, linear heat detectors, often in the form of a specialized fiber optic cable, can detect a sudden rise in temperature and pinpoint its exact location to within a meter. Smoke and air quality sensors constantly sample the atmosphere, sniffing for the chemical signatures of combustion. And above all, a network of hundreds of intelligent, high-definition cameras acts as a constant, unblinking eye. Their video feeds analyzed in real time by artificial intelligence software that is trained to recognize the unique visual fingerprint of smoke or the telltale sign of a suddenly stopped vehicle, triggering an alarm in the control room long before a human operator watching dozens of screens might notice. Once a fire is detected, an immediate and powerful counterattack is launched against its deadliest weapon, the smoke. This is the primary role of the tunnel's ventilation system, a colossal set of lungs designed to manipulate the air with immense force. In many road and rail tunnels, this is achieved through longitudinal ventilation, a series of massive jet fans, resembling the engines of a modern aircraft, are mounted at intervals along the tunnel's ceiling. Within seconds of a fire alarm, a pre-programmed logic, based on the precise location of the fire and the current traffic flow, will activate these fans. They roar to life, creating a powerful one-way wind, a controlled gale that flows along the length of the tunnel. The goal of this critical wind is to push all the smoke and superheated gases in a single, predetermined direction, away from the traffic and people who are trapped upstream of the fire. This creates a clear, smoke-free path behind the fire, allowing for a safe and organized evacuation, and providing a clear point of access for the arriving firefighters. For very long, complex, or bidirectional tunnels, a more sophisticated transverse or semi-transverse system may be used, which employs a separate, full-length ventilation duct, often hidden in a void above the ceiling, allowing smoke to be extracted directly from the location of the fire, while fresh air is simultaneously supplied to the zones on either side, creating a more controlled and balanced atmospheric environment. While the ventilation system fights to create a breathable atmosphere, the second critical priority is to guide the people within the tunnel to safety. This is the science of egress and evacuation. The design of a modern tunnel is a master class in human psychology and crowd control under extreme duress. Emergency walkways are provided along the sides of the tunnel, physically separated from the traffic lanes. The primary path to safety, however, is not necessarily towards the tunnel's exit, which may be kilometers away. In modern twin-bore tunnels, which consist of two parallel tubes, the true lifesaver is the provision of cross passages. These are a series of small connecting tunnels built at regular intervals of every 200 to 300 meters that link the two main tunnels. These cross passages are protected by heavy fireproof doors and are kept at a higher air pressure, ensuring that smoke from the incident tunnel can never enter them. In the event of a fire, a sophisticated system of emergency lighting and illuminated directional signage activates, guiding people away from the smoke and towards the nearest of these cross-passage doors. By passing through this door, evacuees can enter the adjacent, completely separate, and smoke-free tunnel, which immediately becomes a safe haven and a clear path to the outside. Simultaneously, an active attack on the fire itself may be launched by automated suppression systems. While the primary goal is always life safety through smoke control and evacuation, controlling the blaze can prevent a larger catastrophe and protect the tunnel structure itself. In many modern tunnels, this is achieved through a high-pressure water mist system. This is far more effective than traditional sprinklers. A network of pipes running the length of the tunnel feeds a series of specialized nozzles, which, when activated in the zone of the fire, release a fine atomized mist of water at extremely high pressure. This mist has a dual effect. The tiny water droplets have a massive surface area, which allows them to absorb heat from the fire and the surrounding superheated gases with incredible efficiency, dramatically cooling the environment. The rapid evaporation of the mist also displaces the oxygen in the immediate vicinity of the fire, helping to smother the flames. This method is highly effective at controlling the fire's intensity and preventing its spread, all while using significantly less water than a traditional deluge system, which can create vast amounts of vision-obscuring steam that can be a hazard in itself. Alongside these automated systems, a dry or wet standpipe, a permanent network of heavy-duty pipes and hydrants, runs the length of the tunnel, providing firefighters with a ready and reliable source of high-pressure water for their own direct attack. All of these complex, automated, and powerful systems are interconnected and brought together in a single, human-managed location, the tunnel's central control room. This is the brain of the entire operation, a secure, high-tech nerve center that is often located miles from the tunnel itself. Here, a team of highly trained operators sits before a vast wall of screens, maintaining a constant vigil, 24 hours a day. They monitor the live feeds from every camera, the data from every sensor, and the operational status of every fan, pump, and traffic light. In the event of an incident, the system's automated response is triggered, but it is the human operators who manage the unfolding event. They are the ones who use the public address system to give clear, calm instructions to the people trapped inside. They are the ones who communicate directly with the fire department, providing them with precise information on the fire's location and the status of the safety systems. They are the calm human intelligence at the center of the automated storm, the vital link between the machine and the people it is designed to protect. A severe tunnel fire, with temperatures that can exceed that of a blast furnace, poses a direct threat not just to life, but to the structure of the tunnel itself. Concrete, while non-combustible, can be severely damaged by extreme heat. The moisture trapped within the concrete can turn to steam, creating immense internal pressure that causes the surface to violently flake and explode off, a phenomenon known as spalling. This can expose the steel reinforcement within to the fire, which can cause it to lose its strength, leading to a potential structural collapse. To prevent this, the tunnel's inner lining is often protected by a final layer of passive fire protection. This can take the form of fire-resistant boards or a thick, insulating, sprayed-on coating that is designed to shield the structural concrete from the fire's heat for a period of several hours. An even more ingenious solution involves mixing a small amount of fine polypropylene fibers directly into the concrete itself. When the concrete is subjected to intense heat, these thousands of tiny plastic fibers simply melt away, creating a microscopic network of interconnected channels through which the trapped water vapor can safely escape, preventing the explosive pressure buildup and preserving the integrity of the structure. Through this comprehensive, multi-layered, and redundant system of intelligent detection, powerful and strategic ventilation, clear and protected paths of evacuation, and robust structural resilience, the modern tunnel is transformed from what could be a terrifying death trap into a highly controlled and ultimately survivable environment. The complex and expensive engineering of life safety is now considered to be just as vital, if not more so, than the engineering of the primary structure itself. We have now journeyed from the initial deep investigation of the Earth to the final meticulous outfitting of the tunnel for safe human use. But all of this technology, all of this investment, and all of this risk is for nothing if the tunnel does not last for its intended 100-year lifespan. How do engineers fight the slow, relentless, and eternal enemies of any man-made structure? How do they combat the insidious, constant creep of groundwater, the slow chemical decay of materials, and the simple, grinding wear and tear of a century of continuous use? This leads us to the final quiet and perpetual phase of a tunnel's life, the world of inspection, maintenance, and the unending war against time. The breakthrough of the TBM and the final outfitting of the tunnel are not the end of the story. They are merely the end of the beginning. A tunnel, once open to traffic, is born into a state of perpetual slow-motion warfare. Its completion marks the start of a new, silent, and unending conflict fought on a timescale of decades and centuries. The enemies in this war are the most fundamental and relentless forces in nature. The insidious and constant pressure of groundwater, the slow, invisible creep of chemical decay, the grinding wear and tear of millions of passing vehicles, and the simple, inescapable force of entropy. A tunnel is not a static monument like a pyramid, designed to simply exist. It is a dynamic, high-performance piece of infrastructure that must be constantly monitored, maintained, and defended against the forces that are perpetually trying to reclaim the void from which it was carved. The engineering of a tunnel's construction is a sprint. The engineering of its maintenance is a marathon that never ends. The most persistent and dangerous of all its adversaries is water. The subterranean world is a wet world, and the groundwater that saturates the earth is a patient and powerful foe. Despite the multiple layers of sophisticated waterproofing applied during construction, the immense pressure of the earth, the subtle shifting of the ground, and the vibrations of traffic can, over the span of many years, lead to the formation of microscopic cracks in the tunnel's concrete lining. Through these tiny fissures, the groundwater will begin its insidious invasion. This water is not just a nuisance, it is a profound threat. It carries dissolved minerals and chemicals, such as chlorides and sulfates, that can slowly attack the concrete and, more critically, the steel reinforcement bar that is the source of the tunnel's tensile strength. If water reaches this steel, the slow, quiet process of corrosion begins, a cancer that can spread unseen through the structure's skeleton, causing the rebar to rust and expand, which in turn causes more concrete to crack and break away in a vicious, accelerating cycle of decay. To combat this eternal threat, a regime of perpetual vigilance is established. The primary weapon in this fight is regular and meticulous inspection. This is a multi-layered process. It begins with routine patrols, where maintenance crews travel the length of the tunnel on a weekly or even daily basis, looking for the most obvious signs of trouble, active leaks, new cracks, or damaged panels. This is followed by more thorough general inspections every year or two. But the most important event in a tunnel's health regime is the principal inspection, a deep and comprehensive examination that occurs every 5 to 10 years. For this, the tunnel is often closed to traffic, and a team of specialist engineers will use a variety of tools to get within arm's reach of every square meter of its surface. They use specialized inspection vehicles with articulated arms and hydraulic platforms to sound the concrete with hammers, listening for the hollow drum-like sound that indicates a hidden void or delamination behind the surface. They use non-destructive testing techniques, such as ultrasonic sensors and ground-penetrating radar, to peer inside the concrete itself, searching for hidden corrosion or water intrusion that is not yet visible to the naked eye. When a leak or a defect is found, the response is swift and precise. For the common problem of water ingress through a crack, the primary repair technique is injection grouting. This is a highly specialized process where the repair crew drills a series of small holes or ports directly into the crack. A specialized water-reactive polyurethane resin is then injected into these ports under high pressure. This resin is a marvel of material science. It is hydrophobic, meaning it actively repels water, and it is formulated to aggressively seek out any moisture present in the crack. When it comes into contact with this water, it undergoes a rapid chemical reaction, expanding to many times its original volume and curing into a tough, flexible, and completely waterproof foam-like plug. This expanding action drives the resin deep into the finest fissures of the crack system, completely filling the void and creating a permanent, watertight seal from within the structure itself. It is a form of minimally invasive surgery, designed to heal the tunnel's skin from the inside out. As our technology advances, so too does our ability to monitor the health of these hidden structures. The future of tunnel inspection lies in the world of robotics and artificial intelligence, a move away from periodic human inspection towards a state of constant automated surveillance. Engineering firms are now developing autonomous robotic platforms, wheeled or tracked vehicles that can patrol the tunnel during off-peak hours without the need for human supervision. These robotic sentinels can be equipped with a vast and powerful array of sensors. High-resolution cameras capture a continuous visual record of the tunnel walls, while powerful laser scanners create a perfect three-dimensional digital model, a point cloud of the entire structure with sub-millimeter accuracy. By comparing the point cloud from one patrol to the next, sophisticated AI software can automatically detect any new cracks, any spalling of the concrete, or any deformation in the tunnel's shape that might be invisible to the human eye. This allows for the creation of a living, evolving digital twin of the tunnel, a virtual model that reflects the real-world condition of the structure with unprecedented accuracy and detail. Over the span of its century-long life, a tunnel will inevitably require more than just minor repairs. It will need a major overhaul, a comprehensive rehabilitation to extend its life and bring it up to modern standards. These projects are immense undertakings in their own right, often requiring long-term closures and costing hundreds of millions of dollars. A typical rehabilitation may involve the complete removal and replacement of the tunnel's aging mechanical and electrical systems, stripping out the old, inefficient ventilation fans and lighting and replacing them with modern, energy-efficient technology. It may involve structural repairs to the primary lining itself, removing and replacing damaged sections of concrete or adding a new inner layer of sprayed or cast concrete to enhance its strength. It can also involve seismic retrofitting, where an older tunnel, built before the advent of modern seismic design, is strengthened with new ductile materials and flexible joints to ensure it can survive an earthquake that it was not originally designed to withstand. This unending war against time has taught engineers a profound lesson, a lesson that is now baked into the design of every new tunnel that is built: the importance of designing for maintainability. A modern tunnel is conceived from its very first drawing, not just for its primary purpose, but for its entire life cycle. This means creating a structure that can be easily and safely inspected and maintained for the next 100 years. This philosophy manifests in the inclusion of wide, well-lit inspection walkways, of dedicated separate galleries or corridors that house the critical electrical and communication cables, allowing them to be accessed and replaced without disrupting the flow of traffic. It means the careful selection of materials, such as the use of stainless steel or epoxy-coated rebar in the most exposed areas, or the formulation of high-performance, low-permeability concrete mixes. These choices may increase the initial construction cost, but they pay for themselves many times over by reducing the need for costly and disruptive repairs in the future, a recognition that the battle for longevity is best fought with foresight. By embracing this comprehensive philosophy of perpetual vigilance, of constant and technologically advanced inspection, of proactive and precise repair, and of designing for a long and serviceable life from the very beginning, engineers can ensure that these colossal and expensive structures can fulfill their promise of a century or more of continuous, safe, and reliable service. The tunnel, therefore, is never truly finished. It is a living entity, a dynamic system that must be constantly monitored, cared for, and healed to survive its unending and quiet war against the relentless forces of decay. We have now explored the full life of the tunnel, from its conception in the mind of a planner to its violent birth in the deep earth, and through its long life of service and maintenance. But our story has so far focused on the great passages that move us horizontally. What of the tunnels that move us vertically? How do we conquer the unique and immense challenge of creating the deep, complex, and often multi-level station caverns, ventilation shafts, and elevator shafts that are the vital nodes connecting our surface world to the growing subterranean network below? We have journeyed for many kilometers along the great horizontal arteries of the subterranean world, following the relentless advance of the tunnel boring machine and the patient sculptural craft of the sequential excavation method. But these arteries, no matter how long or how deep, are inert and useless without a connection to the world of the surface. They require a heart to pump life into them, and vital organs to connect them to the city above. These are the vertical shafts and the great station caverns, the third and perhaps most complex dimension of the underground realm. The construction of these deep, large volume, and often multi-level spaces represents a challenge that is in many ways greater than that of the tunnels themselves. To create a stable, permanent, and massive void in a single location, often directly beneath the foundations of the city's most important structures, is to concentrate all the risks and all the geological pressures of tunneling into one single critical point. This is the world of vertical engineering, the art of conquering not the journey but the destination. The most fundamental element of this vertical world is the shaft, a deep and cylindrical passage that serves as the elevator, the ventilation duct, and the primary point of access to the deep tunnels below. The methods for sinking a shaft are as varied as the ground conditions they must conquer. In stable rock, the process can be a conventional one, a cyclical process of drilling and blasting a few meters of rock at a time, mucking out the debris, and then lining the newly exposed section with a permanent, cast-in-place concrete wall. But in the soft, weak, and waterlogged soils that lie beneath most major cities, this open-face method is impossible. Here, engineers must employ more ingenious and powerful techniques. One of the most dramatic is that of the caisson, a massive, hollow, and incredibly heavy concrete cylinder, often with a sharpened steel cutting edge at its base, is constructed on the surface. Workers then begin to excavate the soil from inside this cylinder, and the structure's own immense weight forces it to slowly sink into the ground under perfect control, in the most treacherous and water-saturated conditions. The ultimate weapon is ground freezing. A ring of freeze pipes is drilled deep into the earth around the entire perimeter of the future shaft. For months, a supercooled brine is circulated through these pipes, slowly drawing the heat out of the ground until a thick, solid, and completely impermeable wall of frozen earth is formed. This ice wall acts as a temporary circular cofferdam, allowing the workers to excavate the shaft safely and in dry conditions within its frozen embrace. For the creation of the vast multi-level caverns required for a major downtown subway station, a different and even more audacious strategy is required, one that allows the city to continue functioning while a cathedral is being built invisibly beneath its feet. This is the top-down construction method, an evolution of the techniques used to build the launch box, but on a far grander and more permanent scale. The process begins with the construction of the station's immense, permanent, and deeply buried perimeter walls, using the diaphragm or second pile wall techniques we have explored. But then, the brilliant inversion of logic occurs. Before any major excavation begins, the massive reinforced concrete slab that will form the station's permanent roof is cast directly on top of the ground at street level. Once this roof has cured, the surface can be immediately restored, the road can be repaved, the utilities reconnected, and the traffic of the city can resume its normal flow, with the public completely unaware of the colossal project that is just beginning beneath them. Through openings left in this new roof, a fleet of small excavators and loaders is lowered, and they begin to dig out the earth in the space below the roof. When they have excavated down to the level of the station's next floor, the concourse level, they stop, and the concrete slab for that floor is cast. This process is repeated, level by descending level. Excavate the soil down to the next floor, then construct that floor until the entire multi-level station cavern has been built from the top down, a process of hollowing out a building from within, all while the city carries on undisturbed. When a station is simply too deep to be reached from the surface, or when the disruption of any surface level construction is completely unacceptable, engineers must return to the sculptural philosophy of the new Austrian tunneling method. These deep-mined stations are some of the most impressive feats of all subterranean construction. They are created entirely from within the earth, often through the existing running tunnels that have been bored by a TBM. The process begins with the excavation of a series of small parallel pilot tunnels, or adits, which are carefully driven to form the outline of the future cavern's crown. These initial small openings are immediately supported with shotcrete and rock bolts. Then, in a highly controlled and meticulously planned sequence, the pillars of rock between these pilot tunnels are carefully removed, allowing the small openings to be progressively and safely enlarged. The arch of the crown is slowly and methodically revealed and immediately supported, a process of gradually and carefully expanding the void, always ensuring that the ground's natural, self-supporting arch is mobilized and reinforced. This sequential enlargement continues downwards, with the excavation of the benches and the invert, until the final, colossal, and architecturally expressive shape of the station cavern has been sculpted from the solid rock hundreds of meters below the surface, without ever breaking ground. One of the most delicate and high-stakes operations in all of tunneling is the moment of intersection, when the linear path of the TBM must meet the great static void of the station cavern. A tunnel boring machine cannot simply run into a solid concrete wall. The arrival must be a carefully choreographed and prepared event. The specific section of the station's diaphragm wall where the TBM is scheduled to arrive is specially designed and constructed. This area, known as a soft eye, is built not with traditional high-strength steel rebar, but with a special, weaker concrete that is reinforced with fiberglass bars. This creates a section of wall that is strong enough to hold back the earth during the station's excavation, but soft enough to be easily and safely excavated by the TBM's cutter head without causing significant damage to the cutting tools. Furthermore, a massive, flexible, and watertight rubber gasket, a docking seal, is cast into the concrete wall around the perimeter of this soft. As the TBM makes its final approach, it pushes its shield forward until it makes firm and perfect contact with this seal, ensuring that at the moment of breakthrough, there is no possibility of a sudden and catastrophic inrush of groundwater and soil into the station. The deep station cavern is a destination, and its primary purpose is to move people vertically between this new subterranean world and the surface. This requires its own specialized form of vertical engineering. The immense open voids of the station are crisscrossed by the longest and most powerful escalators ever built, complex machines that must operate reliably for decades in a demanding underground environment. The installation of these multi-ton, long-span machines within the complex geometry of the station is a major construction project in its own right. For the very deepest stations, high-speed, high-capacity elevators are required. This necessitates the construction of their own dedicated vertical shafts, which must be perfectly plumb and aligned, and which come with their own unique and complex challenges of ventilation, pressurization, and fire safety. The engineering of this vertical transportation is the vital link in the chain, the system that transforms a deep, isolated cavern from a simple piece of infrastructure into a living, breathing, and functional part of the city's transit network. With the raw structural void now complete and connected, the final and often longest phase of the work begins. The transformation of the cavern from a construction site into a piece of public architecture. This is the architectural fit-out, a process that involves the installation of thousands of individual systems and finishes. A complex web of electrical conduits, plumbing pipes, and ventilation ducts is installed in the walls and ceiling voids. Thousands of lights are hung, their placement and color temperature carefully designed to make the windowless, subterranean space feel open, welcoming, and safe. The science of acoustics is employed, with specially designed wall and ceiling panels installed to absorb the deafening noise of arriving and departing trains. And finally, the durable and often beautiful finishes are applied. The granite floor tiles, the enameled wall panels, and the clear, intuitive signage that is essential for helping thousands of people navigate these complex spaces with ease. This is the final layer of engineering, the human engineering that turns a void into a place. The vertical shafts and the grand station caverns are the vital, beating hearts that connect our sunlit world to the dark, hidden arteries that run deep within the earth. They are the great hubs of the subterranean network, feats of engineering that must combine the brute force of mass excavation with the intricate and delicate precision of architecture. We have now journeyed through every phase of a tunnel's life, from the first deep mapping of the abyss to the final unending war against time, from the relentless, linear march of the TBM to the patient sculptural creation of great stationary caverns. For our final chapter, we will pull back from the specifics of any one method or any one structure. We will look to the horizon, to the immediate future of the subterranean world. What are the next great leaps in tunneling technology? What are the most ambitious and mind-bending underground projects currently being imagined and built around the world? And what does our ever-growing and irreversible reliance on this hidden realm tell us about the future of our cities and indeed of our civilization? We have journeyed together into the deep earth through the complex and ingenious methods that allow us to carve a new world beneath our old one. We now pull back from the immense detail of the present to gaze upon the horizon, to the future of this subterranean realm. The evolution of tunneling is far from over. The next great leap will be into the realm of true automation, where tunnel boring machines guided by artificial intelligence will learn to sense and react to the geology ahead of them in real time, adjusting their speed, torque, and ground conditioning with a subtlety and speed that no human operator could ever match. On the fringes of our research laboratories, we dream of even more radical technologies, of plasma torches and high-powered lasers that can vitrify and vaporize rock without touching it, of nanotechnology and bioengineering that could one day allow us to solidify and stabilize the Earth with microscopic machines. And the ambition of our projects will only grow. Engineers today are seriously modeling the construction of intercontinental tunnels that could one day link continents of vast automated underground networks to transport freight and relieve the pressure on our choked surface roads, and even of deep self-sustaining underground habitats, a final refuge from the growing pressures of a changing climate on the surface. The final truth, then, is that our journey downwards has only just begun. For all of its upward ambition, the city of the future will inevitably and necessarily be a city that grows deeper. We are becoming a burrowing species once more, not seeking shelter in the simple caves of our ancestors, but creating a new and highly advanced frontier deep within the planet. The great work of the tunneler is in many ways the unsung and invisible work of civilization itself, to create order from chaos, to forge a path through the darkness, and to build the quiet, dependable, and unseen foundations upon which all of our noisy, vibrant, and complex surface lives depend. And so the next time you are moving through your city, feel the faint rumble of a train beneath your feet, see the steam rising from a manhole on a cold day, or simply walk upon the solid, dependable ground. Perhaps you will remember the vast, dark, and magnificent kingdom that lies just beneath that thin membrane of reality. A world of immense power, of profound silence, and of the quiet, constant, and heroic engineering that makes our own world possible.